further, where we are going to define how the sequential logic will look like. So sequential logic is also kind of, using combinational circuit as well as some memory element. Memory element is the one where there is a feedback. So either you are keeping it in oscillating condition or you are keeping that in latch condition. Both are actually memory element. And understand one more thing, if we are keeping two such inverters back to back and three such inverters back to back and feedback it, so this one is positive feedback and this one is negative feedback. This is negative because it's giving you the output which is 180 degree phase shifted. 180 degree phase shifted is a negative, right, of the input. So if you are going here, so if I apply like this, so if this is available at x1, x2 will be like this, right. So I am drawing something ideal, although I am not adding propagation delay, but it looks like this one, so which is actually 180 degree phase shifted to each other. That's why each these nodes x1, x2, x3 all are 180 degree phase shifted, so they are negative feedback. But that's not the case for even number of inverters. They are giving you the positive feedback, right, because it will be 0, 360 degree and multiple of that where it's only positive sign. So it's a positive feedback. So in this memory element, it might be positive or negative feedback. Any system is there. Keep that along with the whatever the combinational circuit you have studied. You keep that, and with inputs and outputs, you can realize this sequence of events which you wanted, right. There is one more important thing, which is actually, if you are interested for job after this, it's very popular question, that the difference between latch and flip-flop. Okay, the important thing between latch and flip-flop. This is the most important question people are asking for any digital, digital job is there, digital company, they are going to ask this one. So if your system works with a clock, so there is a clock and it works with a clock. If it is working with the amplitude either 1 or 0 depending on which you are choosing, so amplitude of the clock, so in technical language of digital we do not call amplitude, we are going to call this one as level of the clock. So whatever level you are feeding, logic 1 or 0, depending on that the output is coming, that is known as the latch. Latch is the level sensitive. That's actually word you will see everywhere written in book, but the meaning of level sensitive means it depending on what level you are feeding, whereas flip-flop is the one where it is not working with the level, however it's working with the transition. So transition going from 1 to 0 or maybe 0 going from either 0 to 1 or maybe 1 to 0. So it transition going from 0 to 1 or 1 to 0, that's going to define the flip-flop. So it will give you the output only in this particular time, or it will give you the output on the transition. This kind of thing, flip-flop, has a technical word known as the age triggered. So based on the age going from logic 1 to 0, 0 to 1, it has to be defined, by the way. So with as time progresses, you will learn that where it is level sensitive and where it is age sensitive or age triggered. So we will learn that. So that's the first part. Latch is the one where actually it will latch also, right. This is also the one broad thing. Okay, so this is how the synchronous logic look like. So in sequential logic also there are two categories, one is synchronous and one is asynchronous, but let's go with the whole thing which is synchronous. Synchronous is the one where you are applying the clock at the same time to all the flip flops. Everywhere you are applying same clock pulse which is going from outside. But other case which is asynchronous, you are deriving the clock from something else. So it's conditional thing. This is not conditional, it is coming from outside. Like if you are having a computer, you might be knowing that you are applying some clock from outside, it's keep on running, right? And it's connected to all the flip flops or all the circuits together, and simultaneously it's triggering all the things simultaneously. However, in asynchronous, it might be you are generating inside, so clock might be coming from somewhere else and it's connected. So each these blocks, just treat them as one flip flop. So there are different flip flops are there, so all are actually getting output or the clock from one to another one. This is asynchronous. For the case of synchronous, as I have drawn over here, you are applying the clock simultaneously to all the flip flops together. It's not derived from anywhere, it's tied together. So as many number of flip flops you have. By the way, for clock we are going to have this kind of symbol. I'm going to draw that. So if there is a flip flop, there is one important connection will be, other than input and output, you will have clock. So the clock will look like this one, will have this arrow, and then you are going to say that it's a clock. Sometimes it is not written, then also you have to understand that this is a clock because it's this kind of arrow. If it is like only this one, then this is known as the positive age triggered. By the way, for the case of negative age triggered, keeping all other things as it is, you are going to have one bubble and then this arrow. This is a negative age trigger. So these are the just symbols. Now let's go into the first thing, which is a latch, where what we are doing, instead of an inverter, we are going to make a NAND gate, because NAND gate is the one which is acting as a universal gate. So we can use similar configuration as we have studied. Like now let's observe how it works. By the way, name of this one is SR latch. Latch because it's level sensitive. Whatever input you are going to give, that's based on the level of that one. With time you will understand why I am saying latch only. So one is set and one is reset. So when I want to reset the output, I am going to give logic 1 to R input and logic 1 to S input when I want output to be set. So that's why like set and reset latch is useful, and that's the fundamental, right? And this is also known as the just a latch. Some people call it just a latch. Latch circuit is this one, which is latching the input. Let's look at that, how it works. There are two inputs, let's call them A and B. And outputs I am going to call Q and Q bar. Let's agree on one thing. Wherever Q and Q bar are written are the outputs, and these outputs will be always complementary. If they are not complementary, then we are going to declare that output as invalid. Okay. If Q and Q bar are equal, then it's an invalid output. We are not going to consider that. We are supposed to avoid that. Okay, let's agree on that. Let's start. If A and B, two inputs are there, so there are 4 possibilities are there, right? So let's write down Q and Q bar, right? So what will be the Q? If both are 0, what will be Q? Do we know how NAND gate works? If I apply any input as 0, output is 1 irrespective of other input. Do you agree? So any input is 0, output is 1. So let's look at that. This one 0, this one 0. So outputs are 1. So at the first instance itself we got the invalid output. We should not have this one, right? So, but still we can write it down because we know that this was happen, right? Now what will happen if A equal to 0 and B equal to 1? Now understand, we are not doing anything on static timing or at DC or at 0 time. We are doing everything at after some time. So after the output getting settled, then we have to check the output. So we know that each NAND gate will have a propagation delay, TPHL, TPLH, whichever will be higher, that will be treated as the propagation delay, TP. So after some times only it will give the output. So if I am applying the same theory over here, whatever was the previous Q at time t equal to 0, let's draw that will be easier. So I am drawing Q at time t equal to 0. Q was any value, let's assume 0 or 1, whatever was there. Right now I do not know. So if such kind of things are there, then in simulator it looks like this one, something like this, right? So I am also keeping same thing. At t equal to 0 it is like that, and t equal to, after let's say 1 nanosecond or some time, I am checking. At that time A equal to 0, A equal to 0 and B equal to 1. So I applied this one. So at t equal to 1 nanosecond, of course A and B will not be changed, but what will happen to Q? It requires some time. So let's assume 1 nanosecond is the propagation delay of of a NAND gate. Then after 1 nanosecond, Q will be 1. Do you agree? So if previously if it is 1, then also it will stay 1. If previously it was 0, then it will flip to 1. Do you agree? Right? So this will become 1. Still A and B will remain same. At the same time, let's draw Q bar as well, that how Q bar will look like. So again, this was whatever was there. At that time, I will not have any value. Do you need to see the output at 1 nanosecond? Are you going to see anything at Q bar? Whatever you are going to see, that's just junk. Do not consider that. Why? Because you are seeing the output on the wrong time. What is the time you should see? In this critical path, you will see that to get the Q bar, you have to consider that it's traveling from here to here, right? So on critical path, there are 2 NAND gates are there. For Q, there is only 1. Why I consider only 1? Because A was given 0, right? Not B. To flip Q bar, I need 2 NAND gates to get the correct output. But for Q to be flipped, I need only 1 NAND gate, right? So Q's propagation delay is 1 nanosecond, whereas Q bar's propagation delay is 2 nanosecond. So I need to check the output after 2 nanosecond. So what will happen after 1 nanosecond? After 1 nanosecond, this point will become 1, right? And if both the inputs are 1, then what's the output? 0 for the case of Q bar here. And in between, whatever is there, it's actually just not correct. And later on, whatever you are seeing, that's a stable output. So you need to check the output after 2 nanosecond in this circuit to get the correct answer. And here you can see Q equal to 1 and Q bar equal to 0. That's what we got, right? So you can write it down somewhere. If A and B, 0, 0 was invalid. So invalid. For 0 1 I got q equal to 1 and q bar equal to 0, right. So this is how you have to write it down, but as this is time varying quantity, so it is not correct to just write down q and q bar. That's the wrong thing for the notation. You have to use something called q of t, q bar of t. Everything is actually time moving, so is a function of time. And if I want to say that q of t generally is known as the present state, so because there are actually 3 states are there: previous state, present state and next state. Do you agree? So generally present state is actually the q of t generally, and there for previous state also you are going to denote same thing, but you are going to know that it's previous state, but for the next state you are going to write down q t plus 1, right. So for the previous and present both will have the same notation q of t, but if I want to say that next state, what's going to happen to the next state after t plus time, that's q t plus 1. Sometimes in further study when we are going to learn, then you will write it down q t plus 2, q t plus 3 or q t plus n and so on and so forth. So but this is the standard notation, right. Maybe at the beginning like you might not see these notations in your book, but these notations will be useful when you are going to study advanced courses. So let's study that at the beginning itself and let's use it now itself. So here you can see it's q and q bar only, however we are going to call them as function of t, right. So this was one thing. Now can we comment on after 2 nanosecond q and q bar when a is equal to 1 and b of t equal to 0, right. So after 2 nanosecond, by the way after 1 nanosecond I am going to see q bar t equal to 1, and after getting that value I am going to have this as 0. So after 2 nanosecond. By the way, from this we also learn that the best case and the worst case output, right, or the throughput. Do we know that? What is the worst case and best case throughputs? So best case is 1 nanosecond, because after 1 nanosecond I can see at least one output, right. And q bar is the and both the outputs if I want to check, then it requires 2 nanosecond, right. Or you can say that generalized one, if TP of NAND are there, so for this particular circuit the propagation delay or the throughput needs to be checked after 2 times propagation delay of NAND, right. I can write it down that, and then it might be different also, right. By the way, same thing can be done with the NOR gate also. You can achieve the same thing with the NOR gate also, but it will give you similar answer, but in a reverse way. Just we have to understand that NOR is the one where any input is 0, then output is 1, right. So that is what we are going to see, and that is what we can use it for finding out the same latch, but replacing NAND with NOR. That NOR circuit is given in 4th edition and NAND circuit is given in 5th edition. I prefer NAND gate because NAND is the universal and it's going to be used everywhere, right. Wherever like you are going to write down any code or anything, at the back it will be NAND gate only, right. So this is one thing, and this is 0 1. What will happen if both are 1? Now that's the case, that's the 4th case. If both are 1, then what's the output? Sorry? No, how do you know that it's invalid? No, output are not 0. Previous value, right. So Now I am just again changing this notation as qt plus 1 and q bar t plus 1, so that I can keep it here qt and q bar of t. Because it's not going to change, it depending. So let's assume that, let's assume previous value here, let us assume some value. So which one you like? If you like 0 and let's say 1, if this is 1, 1 plus 1 and 1, it's going to be 0. 0 is coming here, so 0 and 1, 1. It's not going to change this value in any of the condition. If you are keeping both, some values, whatever values will be there for the valid values, by the way, q and q bar with the valid values, whatever values you are going to keep, that condition is going to give you the previous state, right? And here in this case A and B, now by observing this table, we can say that B is the one which is set and A is the one which is resetting the output. So whenever I want to set it, I am going to keep B equal to 1 and A equal to 0. If I want to reset it, I am going to make A equal to 1 and B equal to 0, right? So you can now replace these names with, this was set and this was reset. Note that in the case of NOR, it's going to be flipped. Set will becomes reset and reset will become set. That's why I have started with A and B, right? Okay. I made mistake or? Anyway, so these are the outputs. So let's relook at this function table, how it works. So if set and reset are 1 and 0, actually here he kept it in a reverse way. Anyway, so it's 0 and 1 as the output. If 1 1 are there, then whatever was the previous one. So what this particular function table is assuming, whatever was the previous. So whatever was the previous, it's going to be reflected on the next one, means it's latching the previous condition. In the case of 0 1, it's clear cut 1 0. If it is 1 1, again it's latching. Whatever was the previous, it's going to be latched. If it is 0 0, it's 1 1 or it's forbidden, right? Or it's an invalid state. Different books will have different names, but these are the things. Any doubt thought of when it was actually created. Okay, so now there is extra thing now we are going to add. Let's make it little bit, one level up, where we have one more stage. Okay, so without analyzing, somebody can tell me what will be the worst case propagation delay in this, and after what time I need to check the output. If all of them having 1 nanosecond of propagation delay, 3 nanosecond, right? Because 3 TP of NAND, these 3 will be there on the critical path, or maybe like either this side or maybe other side, right? So any of the side will be there because both are in parallel, right? Okay, now let's proceed further. So for this SR latch, which is again set and reset, to make it work, what should be the value of enable? En is enable. What should be the value of enable in your opinion? If you are giving 0, then irrespective of what input you are giving, the output, both the outputs are 1 and 1. If both are 1, in the case of NAND, output is latched, right? Means it's not going to flip the output on the basis of set and reset inputs. By the way, now this has to be correct. what's your name? Yeah, Bansi. So now this is correct. These notations are correct. You will check that, then you will understand. Okay. So now let's look at that, how it works. So if you are giving 0, then output is actually latched. Means whatever the previous value was there, that will be latched and it's not going to change. It will work when this is 1, right? Then it's depending on the other input. Now let's assume that set and reset. Along with that, I am going to, so before calling it set and reset, let's go with my notations A and B, and let's have third input also. Let's call that one as QT, and I want to check QT plus 1 because that's more realistic. We have to assume some value of present state also of Q, right? Let's assume that so that you can have the correct answer. So in this case, you might have 8 possibilities, right? Right. So now let's look at QT bar T plus 1 as well, right? So what's going to happen if both are 0? If A and B both are 0, what will be the output? It will latch. So whatever will be the previous one, this has to be Q of T. Let's keep it with some different color. It has to be Q of T, and this has to be Q bar of T. Do you agree with this one? If both are 0, irrespective of what input you are giving here, which is already 1 here, so both will be 1. If both are 1, then the output remains at the same place. It's not going to change, right? So I am going to denote them as Q of T and Q bar of T so that I can accommodate next state as QT plus 1, right? Now, if following things are there, where Q equal to 0, I am keeping here Q equal to 0, A equal to 0 and B equal to 1. So we are going to look at the place where NAND gate has an input of 0. So this will be running faster. It's not depending on other side. This is 1 over here. Both are 1, so it's also 0 available here. It does not require anything. So after 1 nanosecond, 1 and 0 both are available. Do you agree with this one? Right? After 1 nanosecond, because this processing was happening in parallel, so the input of this latch part is actually 1 and 0. If this is 1, if this is 0, so Q bar will become 1 after 2 nanosecond, right? This 1 is going over here, 1 and 1 will become 0, right? 0 is coming here, so it's 1, right? So after 3 nanosecond, it's 1, after 3 nanosecond, it's 0. If you look at further 4 nanosecond, 5 nanosecond, this will remain same, right? It's not going to change. So Q remain 0 and this becomes 1, right? So if you look at here, whenever reset equal to 1, it's resetting the output. You see, it becomes 0. Now let's look at the same condition again, but at different inputs. So when it's 0 and 1, this one, when Q equal to 1, and same condition, we need to make this Q equal to 0. Let's see how it goes, right? So if this is 0, this is 1, this is 1, of course enable was 1, so this is 0. If it is 0, this become 1, this 1 will go here, 1 1 will give me 0 after 3 nanosecond. So this becomes 0 and this becomes 1. So Q bar become 1 after 2 nanosecond, Q becomes 0 after 3 nanosecond. Right? Now let's look at the other condition where this is 1 and 0, just to check whether it's giving you what we wanted. This is 1 and this is 0. So if set equal to 1, I am expecting q becoming 1 and q bar becoming 0 after 3 nanosecond, right. So if this is 1, this is 1, I should get 0 over here, 1 0, I should get 1, right. Because of this 0, irrespective of what I am applying here, I should get 1 over here after 2 nanosecond and 1 over here. So after 3 nanosecond, I should get 0 over here. So that will give me 1 and 0. Even if I flip this to something else, let's say in other side where q is 1, right, and other conditions remain same. So in that case, this is 0, this is 1. So one input is 0, so output is 0 only. Oh, sorry, 1 only. This 1 is coming here, 1 will give me 0. So this will remain 1 and 0. So that way we can say that whenever there is a set and reset, means set equal to 1, reset equal to 0. Yeah.
But when the q is 0, then the output will not be 0, 1.
No, we check that, right? If you want, we can try again. Okay. Third row, right? That's what we want to check. So third row, q equal to 0 and set equal to 1 and reset equal to 0, right? This is 1. So 0 1, what will be the output? We done 1. What about this one? 0. Any input is 0. So what is the output? After 2 nanosecond here 1. It flipped to 1, right? This 1 came here, 1 1 will give me 0 after 3 nanosecond. So 1 and 0. That's the settled output, right? Right? You can check with the other condition also. When it's 1, then also it will stay 1 only, right? That's how this was invented as set and reset. SR flip flop is set and reset. The set has to be 1. Maybe that book has made mistake because of this inversion. Actually it inverts. If NAND gate is there, it's inverting, right? So this is actually invert the logic if enable is 1, right? Anyway, by the way, in future you will see that enable will be replaced with a clock and it's running like 1 and 0, 1 and 0, something like that. So we will see that later on, but starting with some generalized thing, it's enable. So whenever this enable is 1, then and then this will work. If it is 0, then it's latching. So depending on the level of enable, this whole system is working, not the transition going from 1 to 0 or 0 to 1, it's working, right? So that's why this is known as the latch, because it's working on the level of the input or the enable, right? Here you can replace that with 1 and 0. So when 1 is there, then in between, so what I wanted to show over here is, if this is a clock which was previously named as enable, so whenever enable is 1 and whatever input I am giving, set, reset, whatever is there, so in between if I am changing it, let's say if this is the input I am giving, something like that, set and reset I am giving like this, then I should have output of logic 1 over here, then here it has to be 0, and here it has to latch because this enable equal to 0, right? So it has to latch whatever was there, and here again when it is 1, it's going to become 1 and then 0. So whatever is happening when clock becomes 1, or it depending on the level of the clock which we are giving, logic 1 or logic 0. In logic 0, it's latching previous thing, In the case of enable equal to 1, which is clock equal to 1, it's going to give you the output. But in the case of flip-flop, that is not going to happen. Flip-flop will look at the output only at, let's say, if it is positive age triggered, in that case, I'm just removing this. In positive age triggered, it will check the input at this point. So both are 0. So this is set equal to 1. So it's going to give me 1 output and it will stay there. In between, whatever is changing doesn't matter. Right? In between, whatever is happening, it's not going to change. We are going to study that, but this was just to explain how the flip-flop will look like. Flip-flop gives the output when it's transition from either 1 to 0 or maybe 0 to 1. Right? And for the latch, what we studied, it's level sensitive. You need 1 to get maintained throughout the operation. Right? So this is what. Any doubt in this one? Yeah.
So in circuit where we are taking the Q of t. So Q of t is represented where?
So he is asking about the significance of Q of t in the circuit.
Q of t and Q of t plus 1.
Where Q of t?
Q of t, yeah, this is Q of t. Sorry, I don't.
So for the third 0 1 0.
0 1 0, okay.
So the Q of t plus 1
Hmm.
becomes 1.
Hmm.
So that is for the seventh condition. So Q of t plus 1 for the third one.
Hmm.
Is the Q of t for seventh one?
7th, what is 7th?
What was
7th row, okay. Here. Hmm.
so that Q of t
Hmm.
which is 1
Hmm.
is comes from the Q of t plus 1 of the third one.
No. It's, look, it does not depend on that. I am saying set and reset. If you look at and observe this, irrespective of what Q are given to you, whatever Q of t you are giving, irrespective of that, output will be 1. Q of t plus 1 will be 1. It depending on the input of the set and reset only. If you are setting it, output is set to 1. If you are resetting it, output is resetted to 0. That is the philosophy. Do you understand?
Sir,
Hmm,
but in
Pita.
the third row when the Q of t is 0, we are getting 1 in the circuit.
So it flipped. So it's not depending on Q of t. That is what I wanted to show over here.
It's not, yeah, previous value will be
So there is nothing like previous value.
when S and R are 0.
Both are 0, then it's a previous value. Not in this case. So inputs are controlling, not Q and QT. That is the case. Inputs are in our hand, not Q and Q bar. Right? Okay. If you want, you can check for this one also. Like if both are 0, it has to be Q of t, Q bar of t. If both are 1, then both has to be invalid state, right? Because both will give the same answer somewhere. Because both will be 0 here. If both are 1, both are 0. So both will be 1 at a time, right? So it's invalid. So I'm just keeping hyphen over here, right? So that's the thing. Okay. Any further doubt or anything? Because this is very important. Okay. No doubt. Charmi, right? Charmi? Yeah.
Sir,
Yeah.
sir, why we are not considering the enable
Hmm.
in the truth table?
Because it's 1 only. If it is 0, so it's a star condition, like when enable equal to 1, then this table is true. If it is 0, then irrespective of what inputs you are giving, if it is 0, what inputs you are giving, the outputs are going to be latched to the previous condition. Do you agree? Because if this is 0, then both are 1. If both are 1, then it's latched to the previous one. So there is no need to check that. If enable equal to 0, whatever you are giving at inputs, qt plus 1 is equal to q of t, and q bar t plus 1 is equal to q bar of t, right? That's the truth table for enable equal to 0. Right? Sorry? No, both are not 1. Okay, both are 1, then it's invalid. But whatever was previous, same thing will stay there. Even if it's invalid, I'm saying same value will stay there. Generally, we'll try to avoid such condition when both are 1. How you can avoid it? Okay. Do you have any solution in this particular structure? Can you think about some way to have, not having that condition? Can you avoid it? That was the biggest invention, by the way, in history, and that's used everywhere, in every flip-flop, every latch. That is the latch which is used. It's very simple, by the way. No switch. If I do this one, will it work? There is no possibility that these two will be same. Maybe some momentarily of time that might happen, right? But do not take the input during that time. By the way, that latch is known as the D latch. Is it there? Okay. Okay. So before going to D latch, let's complete this. So this is the same table which we talked about. So as you already pointed out, 0 means whatever was there, it's not going to change. So S and R both will be don't care, and accordingly when it's 1, you can write down the output, right? So in the case of 0 0, it's latch, 1 is invalid or forbidden or indeterminate. In the case of 0 1 1 0, this is becoming reset and this is becoming set state. Set means q equal to 1, reset means q equal to 0. So that is what we studied, and this was a conclusive remark. But before going to that, so now I am going to, like, this was given in 4th edition. What I taught was the newer one, just to check how old edition is also there. This way also you can make this. You can also make this with NOR gate also, right? So any of the way you can design it, all are like same. So wherever this particular function table is created, that particular circuit is known as the SR latch. Doesn't matter whether you are using AND gate, NOR gate, OR gate, right? There are variety of gates you can use it, and you can realize same circuit or the same function table. Then that particular latch is known as the SR latch, right? Yeah. Just to incorporate the or making the generalized output. Otherwise, look here, if I keep this one table like this one, if I don't keep q of t, then I can only talk about these 4 conditions only, right? What about other conditions? Exactly. So if you want to write down generalized answer, then I need previous and next. So that's why we have to find out one more variable. Yeah. Okay. So this will also give you the same answer. I am not going into that, but when it's reset, it has to be 0. If it is set, it has to be equal to 1, right? Same is here. Might be like it will change. This invalid state values and latch value might be changed here and there, right? Depending on what kind of gates you are using. However, set and reset will stay at the same place. That is what is kept over here. And this table is also known as function table as well as characteristic table. And through this you can find out qt plus 1 in terms of q, s and r. Can we find out that? Can you find out q t plus 1 function? Find out, right? Sorry? why we have taken clock pulse as enable. So that's, look, any other input also you can give, there is no problem. Here we name it as enable, and it's working when its label is 1. When it's 0, it's latching. That is what we also understood, right? You understood that thing? If this is the case, means when 1 and 0 are happening, on that it's giving the output when clock is 1. When clock is 0, it's holding the previous output. So this kind of circuit is very useful in design of anything like processor design or many other things. So such kind of things are latch, which is like we are going to study right after this chapter, where we are going to maybe build bigger system using finite state machine. So where we are going to use latch and flip-flops. Anyway, okay. So what's the Q T plus 1? You can use your K-map, right? And through K-map you can find out the answer. Right? So wherever those indeterminate conditions, those are not going to be kept. We are going to make it don't care. So both will be XX, and you can find out the answer. So that will give me Q, okay, T plus 1 is equal to S times S plus R prime Q. This you can write down somewhere, and you can use it later wherever it's required, right? So this equation is known as the characteristic equation. Okay, so now let's go to the next invention, which was the D-latch. D-latch is the one where such invalid stage will never happen, right? Let's look at that. Again, I am keeping enable even though it's a clock pulse, but in the 5th edition of Morris-Mano, they are keeping enable, so I am keeping the same thing over here. If this is equal to 1, then and then this will work. Otherwise, if I am giving 0, then it's going to latch previous one, right? So now let's write down the truth table, Qt and D only. There is no other input. So there are only 4 possibilities. Zero zero 1 1 0 1 0 1, and I am interested in Qt plus 1. So if both are 0, Qt equal to 0, so I am keeping here 0, D equal to 0. So what's going to happen? This will become 1. Let's assume that this also has propagation delay of 1 nanosecond. Each one of them has the same propagation delay. So how much will be the propagation delay on critical path? Right, 4 nanosecond, because inverter is also added, that has to be included, right? So in that case, okay, sorry, the 0 was already there. So if this is 1, here this is 1, this is 1, so this will be 1 and this will be 0, right? If this is 1 and this is 0, this will be 1 automatically, 1 will go here and this will be 0, right? If you observe over here, the previous one, this one was set and this one was reset. So this one is set and this one is reset, right? So if set equal to 0 or reset equal to 1, Q equal to 0, right? It matches with the whole philosophy, right? So then you can get the answer, but this is just for a sanity check. You can check that whether 0 and 1 is giving you the correct answer or not. So here Qt plus 1 is equal to 0, right? Now look at the case when this is 0 and D equal to 1. If this is 1, this becomes 0, this become 1, this 1 and 1 will give you 0. Because of any input is 0, output is 1, this 1 is fed back over here, 1 and 1 is going to give 0. So after 4 nanosecond, you are going to see 0 over here, right, and 1 over here. Same way, somebody can tell me what is going to happen if one of the input is 1 and another is 0, hence this is 0. What will the output? Qt plus 1 after 4 nanosecond, how much you are going to get it? 0. Yeah, Brushti. What about the third one, fourth one? If both are 1, if this is 1, what will the Qt plus 1? Can you see the pattern? Like last time we were saying set and reset. Actually, by looking at these three values, can you see that Qt plus 1 is exactly equal to D? Right? By the way, name of this D has many names. One of the name is delay latch, right? Another name is data latch. If I want to send data from one end to another end, I am going to use the D latch, where I can send the data, but with considering some delay. So I can send some data serially, right? So serially, if I want to stream out some data, it can be available at other side through this flip-flop, through this latch, right? It's going to give me the same result, right? But after some time. That after some time, in this case, it's 4 nanosecond, right? So after D for delay latch, you will get the output. So Qt plus 1 equal to D only after getting, settled output, and that settled output is depending on how much time is there on critical path, right? Yeah.
So we are adding the inverter so that reset and set don't.
Yeah, they won't become same, right? Okay. So same thing is written over here. So whatever D is there, same will be transferred other side, right? So it doesn't matter. So if you want to set, make D equal to 1, so Q equal to 1. If it is 0, the output is again 0, right? So its graphical symbol look like this one, where you will have clock pulse. If you remember, we talked about this one. So in this case, when we are going to write it down, latch, so either it will be positive or maybe inverted also. Sometimes some people like to use inverted logic only, and it might be like this. If it is a D latch and written like this, where one input is D and one input is Q and one input is Q bar, so what they are writing? So in this case, when there is a bubble over here, then you have to add bubble over here also. Right. If bubble is outside, then you have to compensate that bubble inside this design, if it is there. If it is not there, then it's fine. Then you are not going to add that bubble in your symbol, and it will be like this. But if inverter this bubble is there, then inside those two bubble or the inverted version of the inputs needs to go inside, right? Okay, this is the characteristic table, and through that you can draw the K map. You will see that Qt plus 1 equal to D. That was by observation also. It was easy to find out, right? Right. Okay, so these are some of the symbols for SR. Sometimes S bar, R bar, then you have to add bubbles over here.